Hi everyone, today we're going to talk about reaction profiles. And reaction profiles are ways of representing exothermic and endothermic reactions. So on the screen right now, this diagram is a reaction profile. The only reason that I'm not calling this a graph is because it doesn't have any numbers on the x-axis and the y-axis. So it isn't a graph because of that. It's a reaction profile. Okay, so just to start us off, I'd like you to pause the video now and write an equation. Do me both a word equation and a symbol equation for the combustion of methane. So we have covered the alkanes, including methane, when we looked at hydrocarbons all the way back in Unit 9. So you should be able to show me the reaction of methane and oxygen, which is a combustion reaction. Pause the video here, word and symbol equation. Okay, so the products of combustion are carbon dioxide and water. So our word equation is going to be methane plus oxygen gives carbon dioxide and water. And the methane has the formula CH4. We're reacting that with oxygen. Remember that oxygen is a diatomic compound and therefore goes around in pairs. And the products of combustion are CO2 and H2O. After that, you just need to balance it. Okay, so methane is going to react with oxygen to produce carbon dioxide and water. But in order for methane and oxygen to react, their particles have to collide. Okay, so we've got to have a particle of methane and a particle of oxygen. Two particles of oxygen, if we look at the equation, are going to need to collide in order for this to happen. However, sometimes when they collide, they aren't going to react. So think back to what we did on rates of reaction. Why sometimes does a collision not result in a reaction? Pause the video and have a think if you need to. Why does a collision not always result in a reaction? Okay, it doesn't always have enough energy. The energy needed for a reaction to occur needs to be at least a certain value, and that value is different for every reaction. This is called the activation energy, the minimum energy needed for a reaction to occur. If the energy is greater than that value, it's absolutely fine, okay? But it needs to be at least this value. Okay, so our activation energy is the minimum energy needed by the colliding particles to cause a reaction. And the reason that we need this minimum amount of energy is that in order for our reaction to happen, we have to break the bonds in our reactants. So if I take methane here on the right-hand side, I'm going to need to break the bonds between the carbon and the hydrogens in methane. I've highlighted those in yellow. Those bonds need to be broken. I will also need to break the bonds between the oxygens in the O2s, which I've highlighted in green. So this is why the energy is needed, that activation energy, because for a reaction to occur, the bonds in the methane and the oxygen have to be broken, and bond breaking always requires energy. Always. So bond breaking is an endothermic process. You have to put energy in to break the bonds. Bond breaking, always endothermic. So in a chemical reaction, bonds are going to be broken and new bonds are going to form. So in my reactants, I'm going to need to break the bonds between the carbon and the hydrogens and break the bonds in the oxygen. In my product, I'm going to need to make bonds between the carbon and the oxygens, and bonds between the oxygens and the hydrogens in water. And underneath you can see that clearly. Bond breaking is an endothermic process, and bond making is an exothermic process. Okay, so this is always the case. Every chemical reaction will have an endothermic part, breaking the bonds in the reactants, and an exothermic part, making the bonds in the products. The thing which makes the reaction overall endothermic or exothermic is just which one's bigger. So if you need more energy to break the bonds than you get out when bonds are formed, it will be endothermic. And if you get out more energy from the products than you needed to put into the reactants, then it will be exothermic. We're going to explore how to calculate this mathematically next lesson on Sunday. Okay, so for this particular reaction with methane and oxygen, this is exothermic because energy is taken in to break the methane and oxygen bonds, and energy is released when the new bonds form in carbon dioxide and water. In this case, the energy released in this process is greater than the energy needed in the other process, which is why that it is exothermic. Okay, the products release more energy than the reactants needed. And we can represent this on our reaction profile. Okay, so on our reaction profile, the activation energy is represented by the distance from the reactant line to the top of this curve. This is the activation energy. It's the energy needed to put in and break all of those bonds in the reactants. The difference between the reactants line and the products line is the energy change. Okay, so in this case, because it's exothermic, this is the energy that is being released to the surroundings. And you can always tell from your reaction profile whether it is exothermic or endothermic by looking at the positions of the reactant and product lines. Okay. In an exothermic reaction, the products will be lower in energy than the reactants, because that black arrow there with the energy change, we're showing that energy is being lost. Energy is being released to the surroundings and given out in this process. Okay, so if I look at my two diagrams, on the left, I've got my exothermic reaction, my reactants, and my products. If I look at where they're positioned, my products are lower than my reactants, which means that energy is released, and therefore it's exothermic. In the diagram on the right, my reactants are lower than my products. So that means that the energy there, the red arrow, is the energy absorbed. And if energy is being absorbed, then it is endothermic. And remember, if you are quoted your energy values in numbers, Then if it's got a negative sign in front, like 100 kilojoules per mole like this with a minus sign in front, then that means it is exothermic. And if it's positive, they could show that with the plus sign or they could show it without. If it's positive, it's always endothermic. Okay, so try to use these diagrams that are being shown on the board now to answer this question about the energy profiles. It's asking you to show what is meant by the different labels 1, 2, 3, 4, 5, and 6. Use this one to help you. Pause the video. Okay, so some hints on drawing energy profiles. How do we do it? Well, let's take our methane example, methane burning in oxygen. Our first step is going to be to identify whether the reaction is endothermic or exothermic. Okay, in this case, I'm looking at the number of the energy that we have been given, and it's telling me clearly that it is a negative number, okay, which, as we know, means that this reaction is going to be exothermic. Okay, so I know I've got an exothermic reaction before I start. The second thing I do is I draw my axes and I label them. Okay. The x-axis will always be the progress of the reaction, and the y-axis will always either be the energy or the potential energy. Either is okay. Okay, step number 3 is just to identify my reactants and my products. So I go back to my equation. I know that on the left of my arrow, I've got my reactants, and on the right-hand side of my arrow, I've got the products. And I'm going to draw those on lines here. Okay, so I put my reactants on my first line, and on my second line, I put my products. Now, before I draw my line for my products, I need to decide whether the line is going to be above the reactant line or below. Now, I've already seen that this is an exothermic reaction, and therefore the line is going to be lower for the products than it was for the reactants. Okay, so those are going to be the relative positions of my lines. That's how I decide. The next step is I label my energy change. So I show that this is my change in energy. And I know what my change in energy is because it says so next to my reaction. That amount of energy is 816 kilojoules. Now, it doesn't have to be to scale. You don't have to do it like a proper graph. It just needs to show it. And then the final step in my process is to add the curve like this and just label my activation energy, which is the distance between the reactance line and the top of the curve, the maximum amount of energy I had to put in. Doesn't matter how high your curve goes, just make it sensible, obviously, so it fits on the graph. Okay, so that was step 4 and step 5. It's a good idea on your graph to draw the lines like this, just to show really, really clearly what energy values you're talking about. But you would need to draw those with a ruler, obviously, to make sure that that is nice and clear. Okay, that's everything on reaction profiles. So please go to the Google Doc, which is on Google Classroom, and answer those questions on the reaction profiles.